Can you hear me, everyone? Yes?
Yep.
Okay.
Yeah.
Yes.
Yes.
So today we're going to start chapter 2, which is the basics of the electrostatics. We're going to start by covering the Coulomb's law. We will talk about the superposition principle. We're going to calculate, we're going to do a couple of examples, calculate electric fields from point charges. And if time permits, I'm going to discuss the divergence of electric field, which is closely related to the Gauss law. Okay, so let me write the topics that we are covering today. Okay, so these are the topics we are covering. Coulomb's law. So the very starting point for discussing electric field and electrostatic interaction is the assumption that we have 2 point charges in space. Okay, imagine we have one charge Q here, and imagine we have another point charge, let's call that capital Q here, and we want to see how these 2 charges interact with each other. And that means we want to calculate what kind of force is between these two in terms of the magnitude and in terms of the direction. Okay. So what happens is that the force is exactly along this line. Okay. And the magnitude of the force is given by the Coulomb's law. And that says the force between these 2 charges is a constant, which is 1 over 4 pi epsilon 0 times Q times capital Q divided by R squared. Okay. And R here is the distance between these 2 charges. Okay. This is the magnitude, and the direction is in the direction of R hat. Okay. So if you have 2 like charges, the force is actually in this direction. And that means these 2 like charges are going to repel each other. If the charges have opposite signs, what happens is that they attract each other. Okay. So the epsilon 0, the constant here, is permittivity of free space, and in SI units, this is equal to 8.85 times 10 to the negative 12. The unit is going to be Coulomb over Newton meter square. Okay. So far the assumption is that these 2 charges are interacting in vacuum. Okay. If they are in a different type of material, then there's a slightly separate situation. There are different ways we can include the effect of that material because of the polarization. And one way is that we use a different permittivity for each material. Okay. So that's the topic that we're going to deal with in chapter, as far as I remember, chapter 4. Okay. So this is how two charges interact, okay? And now let's imagine we have more than two charges. Okay, let's say we have a distribution of point charges here, and I'm gonna call this one Q1, and let's say we have more charges here as well. Okay, means let's say we have Q2, Q3, and so on. Okay, now the question is that how these combination of charges interact with each other. Okay, so to simplify the situation, I'm going to call these charges here, the point charge distribution on this side, I'm going to call them source points, okay? And I'm going to call this Q test charge. And I want to look at what kind of forces are exerted from these source charges on that specific test charge, okay? The nice thing is that the way the electric charges interact with each other are independent of each other, meaning that any pairwise interaction is independent of the rest of the charge interactions. And that allows us to use the principle of superposition, meaning that if we calculate the force from Q1 on Q, okay, we can separately calculate the force from Q2 on Q, and so on Q3 on Q, and then we can add up all these forces, okay? So the total force on Q is going to be equal to F1 plus F2 plus F3. And each of these terms, F1 or F2 or F3, are not really dependent of the rest of the terms, okay? So F1 is the force from Q1 on Q, and that is independent of any other charge distribution around Q or around Q1, okay? So that makes the situation a lot easier because we can first calculate the kind of force each of them exert on Q and then add them like vectors. Okay. So F1, if you look at this, I'm going to number this one as well. If you want to look at the F1 is Q1 Q times R. Okay, now because we have a bit of charge distribution here, let's try to be a bit more careful on how we are naming the position of the source charges and the test charges and their location in the space. Okay. Notation that we use in this course and in this textbook is more like this. For any source points, the position that we use prime notation, okay? We use R prime for each of these, okay? And for the test charge, where we are very interested in calculating what kind of electric field is created by other charges, we use the non-prime position. Okay, so let's imagine this is the origin of the coordinate system. If this is R prime, this where we are looking at the position of the test charge or field point, we use non-prime notation. Okay, so any test charge has prime. Any source point has prime notation. Any field point or test charge has non-prime notation, okay? So then the separation or distance between the source and the test charge, we use separation vector for that. So R, script R with this fonts is basically R minus R prime. This is the separation vector. This is the field point. Here where the test charge sits. And this is the source point. Okay, and this notation is convenient, especially in a situation that we have multiple source points and we want to add up the force. Or if we have continuous charge distribution where we want to integrate over the electric field and force created by the source charges. Okay, is it clear so far? Yes, everybody? Okay.
Yes.
So with this notation, I'm going to revise what we have on the top, and here I want to change R with R1 square. And this is the separation vector, the distance, separation distance between Q1 and Q. Okay. And here the R hat is going to be R1 hat, meaning the unit vector in that direction. So if I want to show it on the board, this is the R1, okay? And from Q to Q, this is R2, and so on, okay? Now, following this notation, I want to add up all the forces, okay, and try to simplify the equation, okay, that we are using to add up these forces. And from that, I want to define the electric field, which is a nice way to formulate, mathematically formulate what kind of force each test charge would experience if we put that among a distribution of other electric charges. Okay, so let me get rid of this. I'm gonna get rid of this. Okay. Anyway, this is principle of superposition. All right, so if I want to write F total in terms of this equation, I can, this is a constant, 1 over 4 pi epsilon 0, I take that away, okay? And then for each term we have Q times test charge divided by a separation vector to the power of 2. So I get like Q1, Q R1 square times R1 hat plus Q2Q divided by R2 square, R2 hat, and so on. Okay, and what you see is that we have Q1, we have Q2, and Q3, and so on, but the Q, the test charge magnitude is the same. Okay, so that can be also taken out, and F can be written in terms of Q times all these constants. And so on, okay. And here the assumption was we have just a random distribution of point charges as the source charges, okay? So it can be any random possibility of throwing certain point charges here, okay? And the nice thing is that at the end, whatever force on Q is proportional to the magnitude of the charge Q, okay? And because of that, we can simplify things, okay? And we can write the whole thing here, which is dependent on the position of Q, but independent of the magnitude of the charge. We can write it in terms of E at position R, and note that this position is actually position of the Q, okay? We can name the whole thing here E, and this is the electric field. Okay, so the force is going to be equal to Q times ER. Okay, So by this already the definition of electric field, I guess, should be clear for you. If you put a test charge in a space where we have electric field, okay, the force that that test charge experiences is going to be equal to the magnitude of the electric charge of that test charge multiplied by the electric field. The magnitude of the charge is a scalar. Can be positive, can be negative, but that's a scalar. The electric field itself is a vector. Okay, so the combination of the charge times electric field is going to be a vector with a direction and magnitude. Okay, so electric field is directly related to any possible force that electric charges would experience if you put them in that electric field. Okay, and that comes from the fact that the force is linearly proportional to Q. So we can separate this part, which is electric field, and the charge to calculate the force. Sounds
Professor,
good?
what happened to the small q?
So are these things, I guess it's familiar for you guys, right? I don't
Professor?
hear any response. Is my, okay. And can you, I'm just trying to figure out if my speaker works fine. Can someone say something?
Professor?
Okay, good. I just started hearing you.
I had a question actually. Where did the small q go? Like the small q1, q2?
The small q is here. Oh my God. Yeah, I missed this. These are q. Yeah. Thanks for asking. Yeah, this here. Okay, and note that this electric field is a function of r, the position of the test charge, okay? And all these little r, script r, separation vectors themselves are a function of r.
So, Professor, would it make sense to say that the electric field is just a consequence of all these little charges?
It definitely is a consequence of all these charges. So the way you want to think about electric field is that if you put one single point charge in a space, okay, imagine it creates something around itself, okay, and that is the electric field. It's very stronger if you are close to the point charge, and it gets weaker and weaker as you go away. If you go to infinitely long distance, the effect is going to be zero, okay? So any point charge creates that kind of field. And if you have multiple point charges, each charge creates a field, and at the end, all these fields are added up together. How they are added up? Not like a scalar, but like vectors. Okay, meaning that if you have same charge at 2 points, probably in the midpoint, you can easily imagine the fields are going to cancel out each other, something like that. Sounds good?
Yeah.
Okay. So just one simple example to show that how we add things up using vector addition. So this is a relatively simple example, example 1.2, sorry, example 2.1 from the textbook, that you have 2 point charges, one at this point, charge Q, the other one at this point, charge Q, separated by distance d, meaning that this side is d by 2, the other side is d by 2 as well. Okay, and then you want to calculate the electric field at a position z above this axis. Okay, so imagine this is x, this is z. We have these 2 point charges, and we want to calculate the electric field right at this point. Okay, so if you look at this, you can easily say the field created by Q from the negative x-axis has a direction like this. And the field created by this one has a direction like this, right? So these are two vectors with an angle to each other. If you add them up, the x components of these fields cancel each other out, right? The x components cancel out each other, but the z components adds up, correct? So if this angle is theta, right, the z component of the electric field, I'm going to call that EZ, is 1 over 4 pi epsilon 0. Q is charge of each of them divided by the separation vector to the power of 2. So this is R squared. And the z component should be this field times cosine of theta. Okay. And at the end, the electric field is going to be 2 times the net electric field. So if I use a different color, the electric field, the net electric field is going to be twice the z component of each of them. Okay. So E, I'm continuing here, is 2 times EZ, okay? And then you can imagine R squared, the separation vector to the power of 2 is z to the power of 2 plus d2 over 4. And then cosine of theta is z divided by the separation vector. Z divided by R, which is z over the square root of z2 plus d2 over 4. Okay, combining all these things, the E will be 2q over 4 pi epsilon 0 times, so we have R squared here, we have cosine theta here, we get z2 plus d2 over 4, the square root, and then we have R2 here as well, so it's to the power of 3 by 2. And then we have 1z in the numerator because of the cosine theta. And that is going to be the electric field. This is a magnitude. What is the direction? It's going up in the z direction. So in vector notation, I would multiply the whole thing by z hats. Looks good? Any question? More or less clear here? Easy? Okay. So now let's look at one limiting case. What do you expect if we look at this field, not at a distance close to the x-axis, but if we go so far away, to the point that we are so far away from these 2 point charges, we don't really see the separation between the 2 point charges. What do you expect in terms of how the electric field should be in terms of the distance z and the distance d between the 2 charges?
It gets weaker, right?
It does get weaker, but how does it get weaker in terms of how does it behave in a limiting case that you are going so far away?
Well, the distance z is much bigger than the distance d, so it's basically like the distance d is 0. The charges are in the same place.
That's nice. Yes, the distance. If you go so far on the z, it will appear as if the distance d is 0, right?
Hmm.
And it will appear as if you don't have 2 point charges at distance d from each other. Instead, you're going to see one single point charge with the charge of 2 times q. Because you're going to see these 2 charges so close to each other. Both combined will behave like one single point charge. Does it make sense? Okay, so now let's look at that mathematically. we calculated this electric field as a function of z and d, okay? And then if z is becoming big, we're gonna look at this in the limit of z being way bigger than d. Okay, so in the case that distance z is much greater than d, right? How do you simplify this? You have z in the numerator, which is okay, it's big. But then in the denominator, you have z squared plus d squared divided by 4. This term is going to be much smaller than z. So you can ignore the d squared over 4 as compared to z squared. I would simplify that as E equals 2 times q 4 pi epsilon 0 times z over, I'm going to get rid of the d squared over 4 because that's a small. Here I get z squared to the power of 3/2 times z. How do I simplify this? Z squared to the power of 3/2, okay, is z to the power of 3, and we have 1z in the numerator, so we can simplify this as 1 over z squared. Makes sense? And now look at this. If I want to rearrange this a little bit, I can write it 1 over 4 pi epsilon 0 times 2q divided by z squared times z. And this is exactly the kind of electric field you get if you have the charge of 2q and you are at the distance z from that charge, 2q. Make sense? Okay, so for a lot of electrostatic problems, it's always good to look at these limiting cases, because if you look at the limiting cases, you have 2 ways to check it. One way is your own intuition, how it should be. Second one is mathematically taking the limits, and then you can see if there's any consistency between the math and your intuition, okay? And that's sometimes very useful and also very instructive. You can learn things from it, okay? So, any question on this? No question?
No.
You guys are happy, everyone?
Yeah.
Yes, okay. Nice. So far we covered the Coulomb's law and the electric field, and we did one example. So the next thing I want to discuss is continuous charge distribution. Okay, so we started discussion by looking at the point charges, okay, and that is very nice because mathematically that's very much under control. You can simply say what is the location of the point charge, and you can easily measure the distance between point charges. But in the nature, technically, there's no point charge, okay? So any charge, any electric charge has some dimension. I'm sorry. And so we can always have a volume of charges, okay? And a lot of cases we have some volumes on which the charge is distributed on the surface. And there are cases that we have charges on a line, okay? So point charge is not a real physical, plausible distribution of charge, okay? So what we do is that we can extend the formulation here to consider a situation that we have charge distribution, but that charge distribution is not distribution of point charges, but continuous charge distribution, okay? So let me get rid of this and with 1 or 2 pictures try to explain this on the board. So imagine you have a rather hypothetical distribution like this. We have point charges and some rather real distribution of charges where you have a volume and then you have electric charges distributed over this volume, meaning that if you choose any infinitesimal volume inside this, it has certain charges in it, okay? What we have here, we have, let's say, Qi, and then I can be from 1 to n, and that's number of the point charges we have. What we can have here is we have this infinitesimal volume, the charge here, you can imagine this is dq, and then you can integrate over that volume to see what is the total charges here, okay? So far we looked at this and we formulated electric field at a position R. Let's say this is R, this is field point. Okay, we said ER can be written as 1 over 4 pi epsilon 0 and the summation over Qi times separation vector of the charge R of the charge I to the power of 2 times Ri hat. And I goes from 1 to n, the total number of point charges we have. Okay, so this is technically how you can write electric field at a position R based on the charge distribution you have, point charge distribution. If we move to rather realistic case that we have continuous charge distribution and if our field point is here, we can transform this summation to an integral, okay? And instead of adding the Qi over R square, we can integrate this in a continuous way, okay? And here the electric field is 1 over, I need more space on this. The electric field is 1 over 4 pi epsilon 0, which is exactly the same thing. And now I'm going to change this that summation sigma to an integral. Okay, so instead of Qi, I'm going to use dq. Okay, so this is technically the charge of with the charge within each infinitesimal volume divided by our separation vector square times d tau, because we are doing the integration over the volume, okay? And then of course we have R hat here as well. Sounds good? So these are mathematically exactly the same thing. This is in the discrete regime and this is in the continuous regime, okay? And another way of formulating dq is using the volume charge density, okay? Imagine we have this volume and the charge density may be constant or maybe not constant over this volume, okay? So rho, I would say at the position R prime, okay? We can define this as volume charge density. Okay, and then dq, the charge within infinitesimal volume is rho R prime times d theta. D theta is a volume, rho R prime is the charge density within that volume, and then we got dq, which is a charge in that, okay? So this can be somehow rewritten.
What is it that you wrote before charge density?
This is dq.
No, at the top.
Volume charge density.
Volume. Thank you.
Okay, and then this can be rewritten in terms of rho prime as 1 over 4 pi epsilon 0 rho R prime divided by separation vector square R hat d tau. Okay. By the way, I did a mistake here. Here we don't need d tau because we are integrating over dq. And that's already the element we are integrating over. But if we use a volume charge density, then we should use rho r prime times theta. So the integration technically becomes over the volume elements, over V. Sounds good? Any question on this? Okay.
Somebody had a question in the chat. Somebody asked
Oh, okay.
if the mass is related to the electric field.
Is mass related to the electric field? No, that's a separate thing. You can have a lot of mass, no electric field, or you can have the other way around. A little mass, a lot of electric field. And then electric field, remember that. Electric field is also dependent on the organization of how you have these electric charges. Okay, so technically you can have a lot of negative and positive charges and arrange them in a way that they cancel out each other. Okay, you can have that. So it's not only about how much material and how much electric field you have, it's also dependent so much on the arrangement between them. Sounds good?
Actually, wait, what's the R prime?
What is the R prime? Okay, so the same situation. Any position of the source point is defined by the prime notation. Okay, so if I want to really, this is important. So let me really draw something again here. Imagine this is the origin of the coordinate system. The position of the dq is R prime. Okay, so this is R prime. The position of the field point is R. This is R. And the separation vector R is this. Is the relative position between from the source to the field point. Okay, so R itself is function of both R prime and R. And the integrals that we have here are always over the prime coordinates. Okay. So this is good if we have volume charge distribution. Sometimes we only have a surface or linear charge distribution. Okay, so we need to do a little bit of modification if we have surface or linear charge distribution. Okay, so here I said dq is rho r prime times tau. If we have a surface charge distribution, we usually use sigma r prime for the surface charge density. And then infinitesimal charge is going to be sigma r prime times dA. This is a surface element. Okay, so if we have surface charge density, the integral should be written as ER equals 1 over 4 pi epsilon 0 integration of sigma r prime over separation vector square unit vector dA, and this is on a surface. Okay. Right, so this is for the volume. This is for the volume, this is for the surface. Okay. And if we have line charge distribution, sometimes we have that, okay? Any dq here, so the line charge distribution, usually we say lambda is a surface, a linear charge density. Okay, so lambda is linear. Okay, and then any dq here is basically the lambda r prime times dl prime. Okay, and the integral for the electric field is 1 over 4 pi epsilon 0 times integral of lambda r prime over separation vector, unit vector, dl prime. Okay, so basically we can have three different sort of continuous charge distribution: over a volume, over a surface, or over a line. Okay, for each of them, the basic idea is to identify dq, infinitesimal charge distribution, and then do this integral. But dq itself mathematically should be written different ways. For volume, it's volume charge density times elemental volume. For surface, surface charge density times surface element. And for the line, same idea, but different type of density, linear charge density times length for the linear charge distribution. Sounds good? Okay, so I'm gonna do one example here for the surface, for the line charge distribution. Okay, any questions so far?
I have a question, Professor. For the
Sure.
line integral, why is the line element prime?
I just use prime for no specific reason, actually. You don't need to. This is important to use R prime, but L prime is not that important. Okay.
All right, thank you.
Okay. Any more question? I feel like I'm teaching a little too fast. Slow me down if that's correct.
Also, in the electric field for the line integral, you didn't
Mhm.
put a prime on. Oh, never mind. I see it. It's
Yeah,
just it's just the camera quality.
yeah, by the way, this should be a vector as well. Right. So far, so good? Okay. So, by the way, how's your homework going?
I actually have a question. Where do we turn it in? Do we just email you the homework?
Email
or-
it, yes, I'm gonna send you an email. Basically what you do is that you email me and you CC, that there's a TA who grades your homework. So you're gonna CC her as well.
Okay.
Okay, so you take pictures, okay? Be very careful about the quality of the picture you're sending, okay? Last semester I had a bit of issue. You write it very nicely on a paper, but the quality of the picture sometimes the students send is not that great. Sometimes the light is not good, so it's not legible. Sometimes the resolution is so low, so it's hard to read. Make sure you take a very good picture. If you have a scanner, you could scan it. That's really good. There are certain apps on the phone that you can take pictures, and that really works like a scanner. But for those ones, you want to be careful about two things. The light condition should be good so that you get something of high quality, and then the angle is important. Okay, so make sure you keep it like perpendicular to the page so that you can have something nice, and then it should be okay. Okay. So all the homeworks will be graded by a former student in my class who is a master's student in this department now. And she did an incredible job in this course. So she's grading for you guys. Okay. So homework will be graded by her. And exams, I will grade your exams. Okay. And that's it. So problems are manageable, the homework? Some are a bit challenging.
they're straightforward. One proof was really difficult, I think.
Okay.
If you like didn't, I feel like some of the proofs, if you don't really know how to go about it, they're kind of difficult, but most of them are pretty manageable.
Okay. Do you guys have chance to work with each other? Are you in contact with each other at all?
I know I'm not.
You're
No, not
okay.
me.
Yeah, that's a challenge. No, it's. I'm not in contact with some of my colleagues anymore because of this pandemic situation, and that's not fun at all. So I can easily imagine you guys don't even see each other, right? You're not there, but if you could, I'm a fan of doing that. I cannot force you to do that, right? But if there's any way that you can have, I don't know, email contact with each other or somehow discuss things, as I said before, I'm a fan of that. And for homework, there is an SPS Discord. Okay, Benjamin said that there's an SPS, Society of Physics Students. So that's one way, okay? So again, as I said before, I really encourage students working together on the homework and assignments, okay? And I don't mind if solutions are close to each other, as long as they are not copy-paste. Sounds good? So then we will have a quiz on Thursday. You gotta be very careful, you gotta be here. So around 10:15, the quiz are gonna be online. We're gonna continue the class. You guys can ask me questions from the quiz, okay? The best if you ask question privately, and then if any help needed, I can just announce to everybody in the class, something like that. Okay. Sounds good? Any more questions?
Yeah. Did you already send the email with the CC for the person who's grading the homework, or are you
So
sending
I
that
haven't
later?
did that to you.
Oh, okay. Just
I will.
checking. Just checking. Okay.
I should have, I forgot, but I will. Okay. Cool. Shall we continue here? Okay, there's one example I want to do, and this is similar to the previous example. So previously we had like 2-point charges. We tried to calculate electric field on the z-axis at a position that we are above the point 2 charges. Here, the example is we have a line charge distribution. Okay, so to calculate electric field, we should do one integration. Okay, so let me raise this thing. Okay, so this is example 2.2. We have a surface, sorry, we have a line charge distribution, okay, over x-axis, and the line charge distribution has a distance, has a length of L. Okay, imagine something like this. It starts from negative L/2 all the way to positive L/2. Okay, and the question is, what is the electric field on the z-axis where we are at the position plus c? Okay, so we have this line charge distribution. We want to look at the electric field right here. And the information is that the surface charge density, just to make things very similar to the book, the charge distribution is from minus L to L, so distance of 2 L. Okay, and the linear charge distribution is constant over this length. Okay. distribution is constant, and that is lambda. Okay. So how do you calculate your electric field? It's not a point charge, right? So it's not a point charge that you can calculate one force, one field line, and add it to the next field line. This is a surface. It's a continuous linear charge distribution. Okay. So what you should do technically, integrate it in the form of E at R is equal to 1 over 4 pi epsilon 0 integral of lambda over R squared dl times R hat. Okay, so you should do this integration. Okay, and before everything, we need to be careful. What is R, the field point? What is R, the separation point? And what is R hat? Okay. And these things could be trivial and could be non-trivial, okay? So in certain problems that can be very difficult to identify what is R hat, and sometimes you identify this and it's gonna be difficult to do the integration, okay? One thing you should be careful is that, first of all, the R hat is not a constant vector, okay? So this R hat changes depending on where the integration is happening. So it's not a constant. So not constant. Okay. And R, the capital R, is exactly the position that we are calculating the electric field, but the separation vector, the same idea, is not constant. Usually R is constant, of course, when you are doing this integral, the capital R is constant, but the separation vector is not. Okay. So for this specific problem, it's more or less manageable, okay? But let's write things and first identify what we have and what we are trying to find, okay? So what is the field point here? I want you to answer. The field point is here, positive Z on the Z axis, okay? So the position vector for R is Z times Z hat, and this is a constant. Z, the value of Z is a constant, and Z hat is a constant, okay? What is the prime position that we are doing integration on? The prime position, coordinate refers to the position of the source charges. Where do we have source charges here? On the x-axis, from negative L all the way to the positive L. That's where the R prime is going to get distributed. Okay, so because it's only on the x-axis, I can write R prime as x times x hat. Okay, and the limit of that, where is it starting, where it's ending, will be reflected on the limit of the integral that we are carrying out. Sounds good? And then the DL that we are doing integration on, okay, DL depends usually on how the charge is distributed and where the charge is distributed. In this case, the charge distribution is only on the x-axis, so we can say DL is basically dx. Sounds good? And how about the separation vector? Separation vector is R minus R prime, okay? And that is Z times Z hat, which is a constant, minus X times X hat. Z times Z hat is a constant, but X times X hat is not constant. Okay, this is something that changes within the integral. The magnitude of the separation R is the square root of Z squared plus X squared. And the unit vector r hat is z times z hat minus x times x hat divided by the magnitude, which is z square plus x square. Okay, so these are the variables and basically the position variables that we have. Okay, so this is always should be your first thing. Identify what is a field point, what is a source point, infinitesimal distance that you are doing the integral over, and the separation vector, magnitude, and unit vector as well. Okay, so once we have these things, we can proceed now to do the integral with the proper variables and proper limit on the integral. Okay.
Professor?
So far, so good, yes.
So when we have the R separation, when you go to is the one of absolute value, is that R separation inside the absolute value?
This is absolute value of R separation, yes.
Okay, thank you.
Okay. And by the way, let me show it on the figure as well. So this is, let's say, where the integral is covering from minus L to plus L, but this is like dx for the integral. Okay. And distance of any of these elements all the way to z. Okay. This is the separation vector. Okay. And this distance from origin to here is x. Okay. So this is z, this is x, this is dx, zx, and I think now all these variables are on the figure as well.
Thank you.
Looks good? Okay.
Yes.
So once you do these things, then you are much more comfortable to start the integral. Okay. If you write the integral and just try to put everything here based on the figure and interpretation, it can get messy and it can be confusing. But if you identify all these variables first, okay, and then in the start integral, everything is going to be a lot more clear. Okay, so I'm going to separate this. And I'm going to try hard to squeeze the integration over this space. Okay, so let's see if I can do that. Okay, so substituting all these things in the integral and putting the limit on, I would write the integral as ER equals 1 over 4 pi epsilon 0. The integral is going to be over x. The limit of integral is minus L to plus L. Okay, so this is the limit starting here to here. And the integral is the linear charge distribution. Lambda is constant. And then z square plus x square in the denominator, which is r square. And we got dl, which is dx times r hat. R hat is rather complicated compared to the rest. It's v times z hat minus x times x hat over the square root of c2 plus x2, okay, times dx. Okay, so again, dx is the dl here. The whole thing here is in this bracket is the r hat, okay, and as you see, the r hat itself looks more complicated than the rest of the integral. Lambda is a constant, and r square is z square plus x square. Okay, so this, because of the numerator of this fraction, is going to be technically just two integrals. The best way to do that is to separate them. The reason is that z here is a constant, okay, so that's a constant, but x here is not constant. So in terms of the type of integral we have, each of these terms lead to a different type. So the best way is just to separate them and do them individually separately and then combine results at the end. Okay. So that is basically, I'm just continuing here. So this equal is continuation of that. It's lambda is a constant, I take that out. So lambda over 4 pi epsilon 0 times 1 integral from the first term is z times z hat. Because it's constant, I take it out of the integral and do the integral with a limit of minus L to plus L over the rest of this, which is dx over z2 plus x squared. So we have a square root here, we have z2 plus x2 here, combined it's z2 plus x2 to the power of 3/2. And then the second one, x hat is a constant, so I take that out of the integral, but the x itself is not constant. So the integral is x over again, the same numerator, the same denominator here. C squared plus x squared 3/2. And we've got dx here. Limit of integral is the same, minus L to plus L. And then this. Okay, so basically we have two integrals. They have a bit of different shapes, but both are well-known integrals. You can find it in integration books and everywhere. So this is rather easier. You can do it by integration by part. Okay, x dx over a constant plus x squared to the power of 3/2. This one is dx over this. Okay, so both of them are well-known integrals. Okay, so the solution for each of them, I'm going to continue with the solution here, is, okay, so lambda over 4 pi epsilon 0, bracket open, z times z hat times the first integral is x over this limit is negative L plus L. And the second one is negative x hat negative 1 over this is x hat. Okay, as you see, this one has z hat component, and this one has x hat component. So in terms of what kind of vector field it's going to give me, this term is going to give me a vector in the z hat direction because it's multiplied by z hat. The second one gives me a vector in x hat direction. Okay, so now looking at this, even without substituting anything inside, I would say that the second integral must be 0. Okay, and why is that so? The second one that gives a vector in the x hat direction must be 0. And that's because of the symmetry of the problem. Okay, we have this symmetrically distributed line charge distribution. Okay, I don't expect to get any field that has component in negative or positive x direction. It just has to be 0. Okay, so this one I would already cross it and say it's 0. And of course, if you substitute plus or minus, you're going to get 0 as well. But sometimes you don't really need to even do that. Okay, the first one is going to give me something in the direction of z hat. And so this is non-zero and it will be non-zero as well. Okay, so if you look at this, if we put it plus L, we're going to get a positive term. If we put negative L, we're going to get a negative term. If you subtract it, so obviously it's going to be a non-zero. Okay, so if we do that, the answer is going to be, I'm just trying to see, okay, here I'm going to write the final answer. It's going to be equal to 1 over 4 pi epsilon 0 2 lambda L. Yeah. So we have a Z that will be cancelled out with this Z, the numerator. 2 lambda L times Z times square root of Z2 plus L2 times Z hat. Okay, so this is the final answer. This is the electric field that you get. In terms of the usual constant, 1 over 4 pi epsilon 0. In the numerator, we have 2 lambda L. Okay, and this 2 lambda L, in fact, is the total charge distribution here. Okay, if the surface charge density is lambda, the total charge distributed from minus L to positive L, I'm going to say Q total, is lambda times this distance, which is 2 lambda L. So what we have here is actually the total charge. And in the denominator, we have Z times Z squared plus L squared. Okay. So now we can do exactly the same sort of limiting case check, where Z is so large that we see this charge distribution from negative L to positive L very similar to a point charge. The length L is going to be very, very smaller than compared to the Z we have if you are so far away. Okay, and what we get as a field is the total charge divided by this L square is going to be canceled out. We get 1 over 4 pi epsilon 0 total charge times over Z square. And that's going to be exactly similar to the electric field that you get from point charge if you are far from that. Okay, sounds good? Is it more or less clear?
Beautiful math.
Beautiful math?
It is, yeah.
Yeah, thank you. So again, it's important to first identify any position for the field point, for the source points, and especially separation vector and dl and a separation vector, the unit vector of the separation vector as well. Okay, if you write everything here, okay, nicely, and then start integration, it's going to be manageable. Otherwise, it's going to be super confusing. Sounds good?
Yeah, so R prime will always be the source points.
R prime always refers to the source point distribution, yes. And R refers to the field point. Separation vector is always function of both R prime and R, okay? And the unit vector the same way, okay? It's important to remember the unit vector is not a constant here, because as you move over this, the unit vector direction is changing. The magnitude is always one, but the direction changes. And in fact, for this specific problem, the complexity was actually from the R hat, because the shape of R hat is more complex than the rest of the terms in the integral. Sounds good. Any question on this? No? Okay, it's 10:44. As usual, I could not cover everything that I was hoping to cover. So I'm going to stop here. Okay, so we did example as well. And on Thursday, I'm going to talk about the divergence and hopefully Pearl of you as well. It's a beautiful discussion and it's important discussion. Not difficult, but it's important. So I'm going to cover that on Thursday, the first 45 minutes of the class, and then we're going to have a quiz. Sounds good. The quiz starts at 10:15. And the idea is that you guys finish it in 20 minutes, 30 minutes the most, and then you have another 15 minutes to upload it and submit it. During the quiz, you can choose to stay here. I strongly encourage you just to stay here and ask questions if you have. But when you want to video yourself and record yourself, you can disconnect turn off your camera, and then you can do that.
And it's gonna be one question, right?
It's gonna. I haven't designed that. Usually, either one question or two related questions,
Gotcha.
like part A and part B, something like that.
Gotcha.
It's not going to be like 7 questions and I give you like 5 minutes for each question. Cool. Okay, so you guys enjoy your day.
I do have one question actually, Professor. For the quiz, when we go to submit it, we're submitting both the paper answer sheet, a photo of our paper answer, as well as a video of a description of the answer as well?
Yes.
Okay. Because we can't submit the video directly to the website, we have to submit it through, like, we have to do it through Dropbox or YouTube or something like that.
Dropbox. Yes.
Okay.
So what you can do is that, so you know how YouTube works, you upload, sometimes it takes time for upload. Okay, so this lectures, 1 hour lecture that I upload is 10 gigabyte, takes a lot of time. But the point is that as soon as you click on upload, it gives you a link. You can share that link. Yeah. And if someone's click on that link, YouTube is gonna send a message like it's under process or it's being uploaded. So you're gonna get the link very quick. The same with Dropbox. As soon as you copy your folder, you can take a link to share that, even if it's not uploaded. So don't worry about the upload time at all, at least on Dropbox and YouTube.
All right, that was really what I was wondering about. Thank you.
Okay. Okay. So see you guys on Thursday. Work hard, do the homework, and prepare for the quiz.
Thank you, Professor.
Okay.
Thank you, Professor. Have a good day.
Bye.